Data has been an important part of getting things done for a long time. Ever since we've used computers to help with our lives and work, bits and bytes of data have been the building blocks for capturing and storing meaningful information. Information we can use to understand the world and make decisions about what to do. But bits and bytes are very tiny building blocks, and for a long time that's how we measured data. Although small, those building blocks were big enough for computers to help with a lot of things. Doing math, building spreadsheets, writing, all kinds of stuff. But something incredible starts to happen when those tiny building blocks can be processed in such large batches and so quickly that we're able to use them by the billions, the trillions, or even more. Let's review those building blocks for a minute. The smallest one is a bit. It stands for binary digit, and all that means is that it's enough information for a computer to tell the difference between a 1 and a 0. You could also think of it as an on-off switch. It takes 8 bits, or a byte, to capture one character of data that a human can understand, like a number or a letter of the English alphabet. So the word hat would be 3 bytes of data, 24 bits. From there, bytes are bundled into batches of 1,000, the kilobyte. A typical short email or a half page of plain text is about a kilobyte, or 8,000 bits. Multiply by 1,000 again, and you get the megabyte, enough data to capture a low-quality photograph, about 1 minute of MP3 audio, or a 400-page novel. Multiply by 1,000 again, and you get the gigabyte, 8 billion bits, enough data for an entire album of music or 500,000 pages of text. A typical movie DVD holds about 4.7 gigabytes. You can roughly assume 2 gigabytes per hour of video. A gigabyte is enough data to be really useful. So in modern computing, it's basically the standard unit for thinking about how computers handle data in the 21st century. Common personal computers in 2020 usually hold between a couple hundred and 1,000 gigabytes. So at this point, we have a sense for what the building blocks of data can do for us. But even though we're well into billions of bits, all this is still peanuts, normal, small data. We've been working with data like this for decades, and we're nowhere close to big data yet. It's pretty easy and instantaneous to store, process, and move these amounts of data with just one normal computer, a typical processor and hard drive. And it's pretty easy to transport or stream this much data using the regular internet. To move into the realm of big data, we have to get a little more innovative about how we store, process, and move huge amounts of it. You can stream a movie using a normal computer, but if you're going to predict the weather, teach a computer to recognize faces, or build a program that listens to 500,000 phone calls to find angry customers, you need more. Back in the day, think 2005. To do those kinds of computing jobs, you needed huge, expensive supercomputers. Computing labs would buy machines like the Cray J90 for $2.5 million. Then you needed smart and highly educated PhDs to run the computing jobs. If you had a complex project or a huge amount of data, you'd have to wait in line to access these resources, and when your turn came, it wasn't cheap. In 2010, the Air Force built something they called the Condor Cluster, 1,763 Sony PlayStation 3s all chained together. For a cost of $500,000, all these PS3s worked together as one computer that equaled the power of a supercomputer. This was possible because Sony used commoditized central processors as the base for the PlayStation. This is a key point. Commoditized modular processors can be arranged to perform operations in parallel, breaking massive computational tasks into tiny little pieces. The processors crunch through them all at the same time. A software layer over top the processors unifies and coordinates the inputs and outputs of the computational task, breaking large tasks into many small parallel tasks and running them on commodity hardware was a sign of things to come. Most importantly, consider the cost. One massively powerful supercomputer for $2.5 million versus 1,700 PlayStations for about $500,000. The cost of supercomputing had just been slashed to a fifth of what it was, using computing hardware that was available to anybody. Meanwhile, in 2006, some other important things were going on. The company VMware had introduced the first mainstream broadly accessible application to virtualize computing infrastructure. This application could easily run on top of any physical computer. This was groundbreaking because suddenly you could run many virtual instances of a commoditized processor on top of just one actual physical computer, what you'll sometimes hear referred to as a bare metal computer. You can see where this is going. If you have enough physical computers or physical computing power to do the job, you can daisy chain together as many commodity processors as you want, running them as software and leveraging them all to perform unified tasks in parallel. Running 4 virtual processors on a laptop isn't going to add up to a supercomputer just yet. However, also in 2006, a little company called Amazon was growing rapidly and faced a lot of the scaling challenges many companies do when they rely on technology, which, by the way, last time I checked, is pretty much everybody. The way Amazon innovated through these challenges is a fascinating story on its own, but for now, the important thing is that in 2007, Amazon launched Amazon Web Services, AWS, which allowed anybody with a credit card to access the type of virtualized computing infrastructure needed to perform really big parallel computation on top of commodity hardware. The cloud had arrived. Now you didn't even need PlayStations. All you needed was an internet connection and a little bit of money. Instead of waiting in lines and paying big bucks to a supercomputing lab for heavy-duty computation, you can use AWS to simply subscribe to as much computing muscle as you needed. Of course, you still needed the right software expertise and data science models to leverage Amazon's services, but the underlying hardware needs were changed forever. Big computing was vastly more accessible to anyone in the world. Finally, in 2006, the open source software foundation Apache released the free Hadoop toolset. Apache Hadoop is an application allowing giant datasets to be processed using clusters of commodity computing infrastructure. You can use your own servers or use the cloud to spin up your clusters. Freely accessible to anyone, this application allowed enormous piles of data to be analyzed. Paired with the power of the cloud, large digital assets like video, social streams, and enterprise data troves could be scanned, relationships could be detected, operational visibility vastly increased, and new products and services created. Computers could now see patterns and relationships in data which previously were simply far too large for humans to be able to detect. Where large piles of data had been unwieldy or downright impossible to work with, now there was technology stacked to work with them. A few years later, businesses, data scientists, and software engineers around the world were off and rolling with real-world practical big data applications. So, as of this video, mainstream big data has been up and running for about 10 years. 10 years of continued progress on computing technology and cloud services have exploded into even more potential for innovative and amazing results powered by data. And with big data more accessible, flexible, and practical than ever before, the groundwork is laid for the next step in data-driven evolution, artificial intelligence. In fact, you could say solid big data practice is the single most important prerequisite for anybody who wants to tinker with AI. Despite the technology progress, significant challenges remain for many to tap big data's potential. Managing big data in real time for responsiveness and relevance, and the cost of transporting and integrating big data can still be tough. And a talent shortage is probably the biggest bottleneck. Not just anybody can work with big data. It takes the right team of people. And of course, with any emergent technology, people themselves are always the toughest part of the recipe. There are still things that only humans can do, like building data models, refining and grooming messy data sets, and building and leading the teams necessary to wield the technology. These challenges probably deserve their own video. In the meantime, we hope this has given you a good introduction to big data. If you'd like to learn more, just let us know.